Hey everyone, it's Mr. Jennings coming back at you again with the last video of the Biotech Genetic Engineering portion of the unit. Today we're going to be talking to you about genetic engineering, specifically gel electrophoresis, and other biotech techniques such as PCR. These techniques have been going on in labs for a very long time. They have actually started getting notable changes. Big thing is currently PCR, polymerase chain reaction, for instance, is getting a lot of recent notoriety with the COVID-19 outbreak from the novel coronavirus, because one of the primary ways to detect for that is PCR. So we're going to talk more about that just a little bit. Nothing too lengthy about it because the science is still coming around, and I don't want to be dated by somebody putting up misinformation. So I want to avoid that as best I can. Back and talk about generalities. So let's talk about DNA fingerprinting. So DNA evidence in solving crimes. This is like one of those things that everybody knows that DNA evidence is supposed to be irrefutable in the court of law. It's not perfect, but it does have a very big place. TV shows like Making a Murderer, the various O.J. Simpson documentaries really examine the use of DNA in the courtroom over time. Those were some recent TV shows that kind of put emphasis on that. So we're going to talk about how you can use DNA evidence in a crime scene investigation and most other things. So the primary way you use DNA evidence is gel electrophoresis. And what you basically do here is a technique for separating DNA based on size using an electrical field. It's all based on the basic understanding that DNA is a negatively charged particle. That means if you were to look at it in a term of bioelectrical signals, a lot of particles we deal with are negative. It's a negative particle. So, and what you do is you will put DNA in a gel and you can separate it based on its length, and we'll talk about how that works. Gel electrophoresis is used for forensics, medical diagnosis, paternity test, and evolutionary relationships, just to name a few. And how do scientists find the DNA tick there? Well, they can find trace amount of DNA in a variety of places. Blood, teeth, gametes like sperm and egg. They can find it in hair follicles. They can find it in bone cells and muscle cells and urine samples even, as we see here. Now, to do this test, I'm going to go back just a minute, you have to treat the DNA samples with restriction enzymes that we talked about in the last video when we talked about restriction enzymes that cut DNA up. So when you cut DNA up in these tiny chunks and you load it through the gels, when you apply an electrical field to it, will pull the DNA samples. The lighter samples go further and the heavier samples stay further behind. And what you'd find is after some time, each DNA fragment is going to form within the same mass. So if they share a banding across the gel, they weigh the same. The more bands you have similar to each other, that means they're more DNA are alike, and you have a closer match. Now, PCR is a way we can get around some of the problems here in terms of, do you have enough DNA? So here's the fun thing, or not so fun thing if you want to view it that way. Getting DNA to do a gel electrophoresis can be challenging. So one of the ways you can make a lot of that DNA that you need is through PCR. It was developed in 1983 by Carey Mullis. It's basically DNA amplification. It's used to produce large amounts of DNA from very small amounts of DNA. It uses bacteria found in thermal steam vents of Yellowstone. Bacteria found in these thermal steam vents, they contain a very heat-resistant DNA polymerase, and they found out, hey, we can use a DNA polymerase to put it onto various small samples of DNA, and the reason why it's such a big deal is usually the more you heat up a system, the more it will, react. The problem is if you heat it up too much, things like enzymes tend to denature. However, these enzymes were found in heat-resistant bacteria, meaning they can handle the increased heat. So what you do is you load up the DNA into a thing called a thermocycle here, a very expensive piece of equipment, and over several hours, you get millions of copies of the same DNA strand that you started with. And it's very useful when you're trying to do a lot of bulk testing. Now, gel electrophoresis, as I mentioned, DNA is a negatively charged particle. And because it's negatively charged, DNA is going to move towards the positive side. The size of the DNA determines how far it travels. Again, this diagram here explains what I just spoke about. Large stays towards the back, small goes towards the front. Small pieces are swift, and large pieces are large, and they lag. Had to pause there. There we go. As you can see here, as you run this cell, as you run the DNA, it kind of moves across and basically swims to this gel. The gel is kind of like a gelatin consistency. If we were in the classroom, I could pull one of these out and run one for you. And that was really the plan. Best laid plans of mice and men. So again, you cut the DNA up with specific restriction enzymes, you load them into the gel, and electrical current is going to be passed through the gel, making one side positive and the other side negative. And DNA is going to follow the negative current. Heavier particles just fall behind. As it passes through the gel, basically the layer current is going to separate the DNA base's size. Again, smaller stays further behind. And this is where we get to the forensics portion. So, when you are analyzing an individual that you find, say you found the crime scene sample, and then you're going to compare it to the samples you find. If you have a sample that has for a crime scene, you want to have it be almost all the bands being the same, if not every band. You'll find who has identical banding to the crime scene, meaning they were at the crime scene. If everything else checks out, that means they are the likely suspect to do it. So DNA sample, though, is not perfect. Sometimes DNA can be passed onto an area, and if that sometimes, say somebody walks by and accidentally leaves a hair follicle behind a crime scene, they didn't know it, they may be placed in a crime scene, not aware of it, and they could be unethically walked away because when jurors the term DNA evidence, they know it's irrefutable, supposedly. And it turns out it's largely good, but it could be misconstrued, and it's one of those things you got to make sure you detective pieces. Just because you find DNA at the crime scene doesn't mean the individual is guilty of the crime. Just they're at the crime scene. You need other stuff like motives and alibis and stuff to check. Alright. And you can see how this matches it up. You can also use it for paternity test. When you're doing paternity tests, you want to make sure the bands have half the similarity, because you can half the dad, half the mom. So you want to have about half the banding. Be similar to the kid, as you see here in this one. About half of the dad's bands are found in the daughter, half the bands are found in the son, and no bands found in these two here, meaning they probably have different fathers. This one here, these two have the same dad. And there could be a variety of reasons for that. Alright. So, the big thing here in this unit is this stuff here is current events. This stuff is an ever-changing field of science. Biotech changes dramatically from year to year. So one of the instances, like I mentioned, PCR. PCR is usually for amplification purposes. Because of that amplification process, they are actually able to take DNA samples from COVID patients with the novel coronavirus and are able to determine if they have enough DNA to run a variety of tests on them. And they're actually able to do PCR to help do gel electrophoresis and determine do they have the exact viral genome. It's very interesting, very powerful, and that's also why these tests take a long time, because things like PCR take ever, not really forever, but they take several hours. And they're working on it, and they're trying to get better about it, but they're not perfect. And that's what makes this thing so frustrating. Alright. But overall, pretty straightforward stuff. Hope you all are having a okay time, being safe, and hope you're all staying healthy. But that's it for me today. And that's it for the videos for this week. Again, thank you all for watching. Don't forget, you do have one assignment this week. It is Certified Cultured Beef. And it's about growing beef in a lab. It's current event as well. Take care. I'll see you all around. Adios.